In the next several topics, we will consider second-order linear equations with constant coefficients. So let me recall general second-order linear equations is given by the form ax times y double prime plus bx times y prime plus cx times y equals to g of x. And we have a homogeneous equation when the right hand side g of x here is 0. So we have ax times y double prime plus bx times y prime plus cx times y equals 0. In the previous topic, we learned that whenever we can find two solutions which are linearly independent, then we can capture all other solutions by using linear combination. So from the theory last time, if y1, y2 are two solutions, and I'm talking about solution to the homogeneous equation here. Later on, we will study non-homogeneous equations. But for now, only homogeneous equation. So if y1 and y2 are two solutions that are linearly independent, then y equal to c1 y1 plus c2 y2 is the general solution. And what it means is that this formula c1 y1 plus c2 y2 captures all other solutions of the differential equation. And here c1 and c2 are constant. So recall that two solutions are linearly independent if their ratio is not a constant. So from the theory, in order to solve the equation, we only need to determine two solutions, y1 and y2. However, in general, it's difficult to do so, in fact. Because of that reason, in this section and later on, we will consider the case where the coefficients, so ax, bx, and cx are all constant, meaning that we consider this, and we're gonna rewrite as little a y double prime plus b y prime plus c y equals 0, where a, b, c are real numbers, are constant, and that's why the name equations with constant coefficients. We actually saw such an equation before in the very first topic, topic 1. So to determine y1 and y2, the two solutions, we will use the ideas from topic 1. So to find y1, y2, we first look, actually, we look for values are for which y equals to e to the r times x is a solution. So, well, we take the derivative, keeping in mind that r is a constant. So y prime is r e to the rx. Y double prime is r squared e to the rx. And now we plug into the equation. And this is the equation we want to solve. So let's plug those derivatives in. We will have a times r squared e to the rx plus b times r e to the rx plus c times e to the rx equals 0. And we want this to be true for all x. But we see that all terms have the common factor e to the rx. So divide by e to the rx. We have the equation for r, a r squared plus br plus c equal to 0. And once we solve this equation, we will have the values of r. This equation is special and it's important to solve the differential equation. So we call this the characteristic equation. Characteristic equation of the ODE. And the ODE that we're talking about is this ODE. A y double prime plus b y prime plus c y equals 0. Then the characteristic equation is just ar squared plus br plus c equals 0. So by knowing the ODE, we can write out the characteristic equation easily like that. Now we can solve this quadratic equation by factoring or by using the quadratic formula. And as I mentioned earlier, you should know both because we will need both later or sooner or later. But if you solve it, then we actually have 3 cases of the values of r. Have 3 cases for, we will say, the root of the quadratic equation. The values of r are called the root. And you should know that from your college algebra. Case 1 is that the equation has 2 distinct values. So distinct roots are 1, are 2. And so distinct means that R1 is different from R2. This case will be in our topic 11, and it's easy to do because once we have R1 and R2, then we have 2 solutions. Y1 equals to e to the R1x and y2 equals e to the R2x. You can check that the ratio y2 divided by y1 is e to the r2x divided by e to the r1x, which is, we can simplify as e to the r2 minus r1 quantity times x. And because r1 and r2 are different, the ratio is not a constant. So y1 equals e to the r1x, and y2, which is e to the r2x, form a basis for the space of solutions. Then we know the general solution of the equation. That's the first case when we have distinct root, one different from r2. Now the second case is when we have repeated root, meaning that we have r1 and r2 are the same. So in this case, when you factor, you have the same factor. We will be interested in how many times a root is repeated, so we should write r1 and r2 as well, even though they are the same value. In this case, y1 is e to the r1x, but we cannot take y2 to be e to the r2x, because if you take y2 to be e to the r2x, this will be the same as y1, and so the ratio would be 1, would be a constant, and y1 and y2 would be linearly dependent, so they will not form a basis of solution. So in that case, we need to take y2 to be something else. So in fact, it turns out y2 is x times y1, which is e to the r1x. We will discuss case 2 in topic 12. I will explain why such a y2 is a solution, and then we will look at examples. The last case is when we have complex root. In this case, we won't be able to factor, but we need to use quadratic formula, and it turns out we need to take square root of a negative number. So how do we handle this? That will be in topic 13. So let's go back to case 1, and that's the content of topic 11. Distinct real roots of the characteristic equations. So we consider, let me summarize here. Consider the ODE, a y double prime plus b y prime plus cy equals 0, where a, b, c are numbers, are constant. Then we have the characteristic equation. So to solve this, I will just write better. We look for solution. Look for solution of the form y equals e to the rx. Then you don't need to take the derivative again and plug in and simplify. We did that already, so we can just write down the characteristic equation. Will be a second derivative, then we have r squared, plus b first derivative, then we'll have r. And without derivative, we just have the constant. And in this case, we solve this. And to get distinct root y1 different from y2 here. And we know y1, y2. We know the general solution. If we have initial condition, we can use initial conditions to determine C1 and C2. So let's look at examples. Consider the ODE y double prime plus y prime minus 2y equals 0. First, find the general solution. So to find the general solution, as before, we look for a solution of the form y equals e to the r times x. And then we have characteristic equation. You may pause the video and write out the characteristic equation yourself. If you do it correctly, then you have followed the lecture very well. But in any case, the characteristic equation is whenever we have y double prime, we replace it by r squared. So r squared plus r minus 2 equals 0. We can solve this by factoring or by using quadratic formula. In this case, we can actually factor like this. Always, after you have factor, you should double check to make sure that your factors are correct. I'm just checking it quickly here. Distributing r squared minus r plus 2r give me plus r, and then 2 times negative 1 is negative 2. That's correct. So I have r plus 2 equals 0, and then r minus 1 equals 0. And two roots. The first one, r1 in negative 2, and the second one is denoted by 2. Now it does not matter which one you denote by r1 or r2. Your answer would turns out to be the same. So y1 is e to the r1x, so e to the minus 2x, and y2 e to the x. And by the way, we should mention that they are different here. The two roots are different. And you don't need to verify again. Whenever we have two different roots, y1 and y2 form a basis for the space of solution. So you can just write out general solution is y equal to c1 y1, which is e to the minus 2x, plus c2 y2, which is e to the x. Where C1, C2 are constant. This general solution captures all other solutions. Now B, find solution with initial condition. For initial condition, as we saw earlier in the last topic, there are two conditions here. One is for the function and one is the derivative. So for example, we have this y0 equal to 1 and y prime 0 equal to -1. So how do we do that? How do we use these initial conditions to determine C1 and C2? Well, let's go back to the general solution here. The first condition says, the first initial condition says that when x equals 0, y equal to 1. So we just plug in x equals 0 and y equal to 1. X equals 0, y equal to 1. We plug in, we will have right here 1 for y equal to C1 e to the x is 0, so e to 0 plus C2 e to the 0 as well. So we get 1 equal to C1 plus C2. Now the second condition, second initial condition is x equals 0, y prime equal to -1. So how do we do that? How do we use this? Well, we need to take the derivative of this general solution because the initial condition involves derivative. So let's compute y prime first. Taking the derivative of this, keeping in mind that C1, C2 are constant. So we have C1 times e to the minus 2x times -2. Don't forget the chain rule. And C2 times e to the x. The second one is just e to the x, and the derivative e to the x is the same e to the x. And now we can plug in x equals 0 and y prime equals to -1. So we have -1 equal to C1 e to the 0 times -2 here and plus C2 e to the 0. Then we get -1 equal to C e to 0 is 1, so minus 2C1 and plus C2. We have two equations here. This is the second equation for C1, C2, and this is the first equation. How do we solve for C1, C2 from these two equations? You may use any method you learned from college algebra. There are two methods, substitution or elimination. You can choose your favorite method. Let me do elimination here. So I'm gonna try to eliminate C1. So I multiply equation 1 by 2 and then add with equation 2. So 2 times equation 1 will give me what? Everything we need to multiply by 2. So we have 2 equal to 2C1 plus 2C2. This is 2 times equation 1. Give me this. And now I add them up, add the two equations. Add the equations. Then I have -1 plus 2 is 1. negative 2c1 plus 2c1 should be 0, and that's what I want because I want to c1, and then I have 3c2 here. Now I can solve that c2 is 1/3. Now to find c1, I just substitute c2 equal to 1/3 into either equation, say equation 1. Then we will have what? Equation 1 says that 1 equal to c1 plus c2, c2 is 1/3. So from here, I solve for c1, which is 2/3. Now knowing c1 and c2, we have the answer. Y equal to c1 2/3 e to the negative 2x plus c2, what is 1/3, times e to the x. Okay, so let's explain here. Our general solution is c1 e to the negative 2x plus c2 e to the x. Once we know c1 and c2, we just plug in and we have the answer, okay, which is over here. So 2/3 e to the negative 2x plus 1/3 e to the x. All right, let's look at another example. In this example, we will solve the initial value problem. Meaning that we have both the ODE, 6y double prime minus 5y prime plus y equals 0. This is our ODE together with initial conditions. Y0 equal to 3 and y prime 0 equal to negative 2. You may pause the video and try yourself. Now first we look for solution of the form e to the rx. Now the reason that I keep writing down this sentence is to make sure that you understand and you remember once we know R1 and R2, we plug in the formula to get Y1 and Y2. But I'm not gonna take derivative. I just write out the characteristic equation right away. Characteristic equation. That is 6r squared minus 5r plus 1 equals 0. Again, to solve this, you can use quadratic formula or try to factor. Now, if you try to factor and you cannot do that after, say, a minute or two, then you should use quadratic formula. And maybe to remind you of the quadratic formula, let me do this here. And by the way, here's a quadratic formula. R will be minus b plus minus square root of b squared, and I should put parentheses around these values, p squared minus 4ac, and everything must be divided by 2a. That's quadratic formula. So let's write it down. We have b here is -5. The whole thing is b. And the whole thing here, 6 here is a. And the plus 1 is c. So we have minus of -5 plus or minus square root of -5 square minus 4ac or divided by 2a. Computing this, we have 5 plus or minus square root of 25 minus 24 over 12. So we have 5 plus or minus square root of 1 over 12. So we have two cases here. Let's write R1 with the plus square root. So we have plus 1 over 12, 6 over 12, a half. And R2 with the minus square root. So we have minus 1 over 12, which is 4 over 12. So we get 1/3. So y1 will be e to the a half of x. And y2 e to the a third of x. These two roots, R1 and R2, are distinct. And so y1 and y2 form a basis of the solution space. Then we have a general solution. Y equal to C1, y1, e to the a half x, plus C2, y2, e to the a third x. Now our next steps are to determine C1 and C2 using initial conditions. So recall the first initial condition is y0 equal to 3. That is, when x equals 0, y equal to 3. So we have 3 equal to C1 e to the 0 plus C2 e to the 0. Now keep in mind, we need to plug in the values of x and the value of y. For the example here and the last example, x equals 0. But sometimes x may be, say, 1. Then you need to plug 1 for x. Okay? Remember that. And we have 3 equal to C1 plus C2. This is equation 1 for us. Now, the second initial condition is y prime at 0 equal to -2. Meaning that when x equals 0, y prime equal to 2. So in order to use this, we need to calculate y prime from the general solution right here. Using the chain rule to compute the derivative, we have C1 e to the a half x times a half. Plus C2 times e to the a third x times a third. We need to use the chain rule for the derivative there. Now we set y prime equal to -2 and x equals 0. We plug in 0. We have C1 e to the 0 a half plus C2 e to the 0 a third. So simplify, -2 equal to a half C1 plus a third C2. This is our equation 2. We have two equations to solve for C1, C2, which means we have a system of equation here. That's what you learn from college algebra, system of equation. Now, how do we solve this system of equation? Again, we can use substitution or elimination. But before you do anything, let me ask, are you comfortable working with fractions? Would you like to work with fractions more than with whole numbers? I guess the answer will be no. You would prefer whole numbers, right? So because of that reason, we need to get rid of all the denominators here by multiplying everything by 6, I would say. Then I will have minus 12 equal to 3 C1 plus, I need to distribute 6 to each of the term here, plus 2C2. And this is my new equation 2 instead of the previous one. It would be easier to solve. Okay, so let me recircle this. This is my new equation 2. Equation 2 and equation 1 like that, and you can use substitution or elimination. Let me use elimination. I want to eliminate C1, so I want to have from here minus 3. So I multiply equation 1 by minus 3. So negative 3 times equation 1. Then I would have every terms gets multiplied by negative 3. So negative 9 equal to negative 3C1, negative 3C2 as well. Add them up, we get negative 21 equal to the C1 cancel out, and I get negative C2. So solve for C2, we get C2 is 21. Now plug into equation 1, which says that 3 equal to C1 plus C2, but C2 is 21, so we can solve for C1 is what? Negative 18. And finally, we have the final answer, y equal to C1 minus 18 e to the, if you recall, C1 e to the half x plus C2 e to the third x. So C1 e to the half x plus C2 21 e to the third x. And this is the solution to the ODE with the initial conditions. So this is the end of topic 11. In the next video lecture, I will discuss the case where we have this repeated root for the characteristic equation.